right.
Everything looks good?
Yeah, everything looks good. We hear you very well. So, next talk is given by Mike Norman from Argonne National Lab. Mike, please.
Thanks, Jimmy Al and the organizers for this opportunity. I'll give a bit of an overview since I'm giving the first of, I think, 11 nickelate talks at this meeting. The list here is the fact that when I put this thing together, I realized since 2016, I've done 20 papers in this area. So this has taken up quite a bit of my research capacity the last 8 years. So here are some, but not all of my partners in crime. John Mitchell in 2015 sort of approached me about thinking about these nickelates because of some data his postdoc, Junji Zhang, had been taking. And I got very fortunate at that time. I had just got a postdoc start with me, Antia Botana, who's very gifted. And her and I launched in to help John and Junji with their data, and then later some data Danny Phelan's. And then after that, some data that we interpreted with Mark Dean's group at Brookhaven. And then we had some help on the DMFT front from Andy and Hyewon Park. And Harry is a student of Antia's who just finished up as head of the Flatiron, who's done some of the latest theory work on this. So, when cuprates came out, I mean, by today's standards, right, they're not that high, 30 Kelvin, but it didn't take long to go up to 160 Kelvin. And so since then, people were thinking about, well, are there cuprate analogs out there? And obviously, one of the first things that people thought about were nickelates. And the 214 nickelate, as usual, hole doping is always easier than electron doping. And so the first thing that was explored was to look at the hole dope side of the 214 nickelates. In fact, I think one of the first theory stripe papers I actually saw on this done was by Jan Zanen, who unfortunately passed this month. But if you look at the phase diagram, what you see is a series of stripes and checkerboard phases, and the material is basically insulating. You have to push beyond 100% doping to formal valences less than D7 before you even start to see metallic behavior, and you start to see something that looks like Fermi arcs. But to date, no evidence for superconductivity in these doped 214 nickelates. But since then, we know a lot more about the phase diagram. So now people have been able to map all the way out from D9 configuration, where nickel is 1+, all the way out to the perovskite D7, where nickel is 3+. And of particular interest are the line phases. You have the N=1 Rudelson-Popper phase, which is 214. You go to bilayer 327, trilayer 4310, all the way out to the perovskite, which can be considered as infinite layer. And then you can do what's called topotactic reduction, and you can get the 113 to reduce to 112, 4310 reduced to 438, and the 327 to reduce to 326. And effectively allows you to sort of look at the electron dope side relative to the 214 phase. And this is something that we started working on in 2015. And of course, you get these line phases, and a particular interest is the 438, which is the reduced variant of the 4310, where the lanthanum compound was a stripe-ordered insulator, but the praseodymium compound was a metal, and in fact, its transport properties look very reminiscent of overdoped cuprates. So the way this happens is that one uses hydrogen, called topotactic reduction, to strip out the apical oxygens of the material. In the trilayer case, this leads to 438. On the right, this shows you sort of how these things are grown by single crystals. You basically vary the oxygen partial pressure. You start with a 214 phase. You have a very narrow stability range for 327. This is why in the new 327 work is very hard to get single crystals. You typically then go to the 4310 phase, and then at high oxygen partial pressure, you end up in the perovskite. This phase diagram gets pushed to higher oxygen partial pressure when you go from lanthanum to praseodymium neodymium, which is why sort of things are always easy to make in lanthanum and becomes harder to make as you go to from lanthanum to praseodymium to neodymium. So the infinite layer nickelate, believe it or not, which is gotten by topotactic reduction of the perovskite, actually predates the Bednorz-Muller discovery of high TC cuprates. Work goes back to 1983 from several groups, including Mike Hayward's group. And what happens here is you start out with a valence of 3 minus 1 over n, where n is a number of nickel oxygen layers. And by stripping out the apical oxygens, you go to 1 plus 1 over n for the nickel valence. And so, of course, obviously the most drastic change is when you go from 113 to 112 because you're changing the valence by 2 units. And this is why there's always been materials problems with these 112 nickelates. So people have been thinking from a theory perspective about these nickelates for quite some time. One of the first papers was by Morris Rice and collaborators back in 1999 with the ideal that they felt that lanthanum nickel O2, which is a 112 phase, would be a charge transfer antiferrometric insulator just like calcium copper O2. And then if you doped it, you would get spin zero doped holes very, very similar to cuprates. And so to get perspective on this, I bring up the famous Zonin-Savatsky-Allen phase diagram, where you have a charge transfer energy between transition metal 3D and the oxygen 2p states, and then you have the Coulomb repulsion. And so if the Coulomb repulsion is less than the charge transfer insulator, you're in the Mott regime. If it's greater, then you're in the charge transfer regime. So Warren Pickett and student pointed out back in 2004, though, that lanthanum nickel O2 is not as close to copper 2 plus as you might think. And in particular, what they notice is because of the infinite layer structure, the C-axis coupling is much stronger than what you see in a typical cuprate. Plus, you have pockets formed from the 5D orbitals of the lanthanum site, and then the 3z squared minus r squared states are closer to the Fermi energy than the cuprates. And so this makes these nickelates a little bit different than cuprates. And so the way to think about this, of course, is that the nickel is 1 plus. It also has an ionic charge 1 less. And so the net result is relative to copper, the nickel 3D bands float up in energy. And so this not only increases the charge transfer energy between the nickel and oxygens, it also leaves an overlap of the nickel 3D bands with the rare earth 5D bands. And this is a difference from cuprates. So the surprising thing is, of course, we all knew about these things for a long time. In fact, if you go to Mike Hayward's thesis, he actually doped these 112 nickelates. But it took Harold's great discovery in 2019 to realize that these materials were actually superconducting. And superconductivity was not impressive, maybe around TC of 15 Kelvin, but people have been able to push it up higher by pressure and other tricks, just like people had done in cuprates. And what, again, you do this topotactic reduction. The nice thing about using films is that the substrate provides an orientation. The problem in perovskites is cubic, and so when you reduce the bulk material, then you have C-axes pointing all over the place. Whereas if you grow on a film, then of course the substrate aligns the C-axis. And the net result is that you get much higher quality material if you do it in thin film form than if you use the bulk. The other interesting thing is, as Harold showed, as a function of doping, you have tendency to go from a negative Hall number to a positive Hall number. And this can be understood theoretically. We treated this in our original theory paper on this in 2020. At the zero doping level, you have these 5D electron pockets from the 5D orbitals of neodymium. Those lead to a negative Hall number. And then the assumption, of course, is that the whole dope stuff coming from the nickels are probably incoherent. But as you dope, you depopulate these 5D orbitals. The hole-like nickel oxygen states start to participate in the Fermi surface, and therefore you switch to a positive Hall coefficient. And then when you map out the phase diagram, you get something somewhat similar to cuprates, roughly around 12% doping. You start TC turns on, and then it ends at 25% doping, which is exactly the doping level where superconductivity disappears and recuperates. And you have sort of dips in the middle, what you think might actually be some sort of maybe signature of charge ordering, like what happens in recuperates. The deal, of course, is on the underdope side, you get something that's sort of weakly insulating. You don't see any real evidence for Mott insulator formation like you do in recuperates. And then you typically get weak insulating behavior on the overdope side, unlike recuperates, which you typically get a pretty good metallic state. So theoretical ideals have sort of been in two camps. One is, yep, you get charge transfer energy is larger in these nickelates and recuperates, but the basic physics is somewhat similar. You get 3D2B mixed states. The doped poles tend to be spin zero. They tend to reside in the x squared minus y squared orbitals. The effect of the rare earth 5Ds are basically to act as self-dopants. You get super exchange, but it's reduced relative to what you see in recuperates, but it's relevant. The second scenario is that you have something more like a Mott thing. That is, the 2p orbitals, oxygen 2p's don't participate so much, so you get more of the Mott type picture. 3z squared orbitals come into play, so it's more like a Hund's metal. And then, of course, the 5D rare earth orbitals can screen the nickel D, so you get some sort of condo physics coming in and play as well. And so this is sort of the second camp, and it could well be that both aspects apply to the real material. That is, you're sort of an intermediate regime between this charge transfer recuperate scenario and this Mott Hund's metal phase, and you're sort of in this intermediate regime, which of course makes it more difficult to treat theoretically. So just a reminder, you do get a recuperate-like nickel 3D x squared minus y squared band near the chemical potential. If you look at the T hopping integral, it's about 80% of what you see in calcium copper O2. T prime over T ratio, where T prime is the next near neighbor hopping ratio, is identical to recuperates, but the charge transfer energy goes up by almost 2 volts when you go, say, from calcium copper O2 to lanthanum nickel O2. As was noticed early on by Matthias Hepting, if you look at lanthanum 112, it has no pre-edge peak and oxygen K-edge. But then again, LISCO doesn't have a pre-edge peak also in the insulating phase, and you have to dope to get a pre-edge peak to show up in oxygen K-edge, which would indicate the participation of oxygen holes. I contrast this with what we saw in the reduced trilayer nickelate, where you actually have a pretty pronounced lanthanum pre-edge peak at the oxygen K-edge for this lanthanum 438 material. As you dope, this is shown by Barrett Gouge. As you dope, you do start to see an oxygen K-edge pre-edge peak emerge. It's pretty weak. It's smeared in energy, which is probably due to disorder. We saw the same effect in some data we took with Mark Dean's group at Brookhaven. You can see that you get a pre-edge peak, but it's pretty attenuated compared to what you get. But when you go to the 438 material, which is sort of like 1/3 whole doping relative to D9 recuperate, you see a pretty substantial pre-edge peak emerge, which is shown in blue here on the right. You can look at nickel L edge, and what you see is a nice fluorescence line. A fluorescence line is if you look at energy loss versus incident energy, you see a diagonal feature in the spectrum. You see rather pronounced fluorescence line in lanthanum nickel O2. We see this as well in the 438 in both sigma and pi polarization geometries. This is a typical signature in transition metal oxides of nickel 3D oxygen 2p mixing. There's also a charge transfer feature that you see in sigma polarization up at around 4 to 5 volts. This is your charge transfer feature. So as you can see, the charge transfer gap is significantly larger in the nickelates than in the recuperates. You can obviously see this charge transfer feature much more pronounced in oxygen K-edge. On the left, you see the 438, where you see the oxygen features sort of range between 4 and 8 volts. Whereas you can see that although the upper edge of this is pretty much the same in LISCO, the lower edge goes down to about 2 volts in LISCO. And the FL feature is, again, the fluorescence line. So if you look at lanthanum 438, it's a stripe insulator, but the presenting compound is a metal. Interestingly, you get a 3-period diagonal spin stripe state, just like you get in 2,1,4 nickelates when you whole dope them. It has a sort of up-down zero pattern. And within the trilayers are stacked. You have up, down, up stacking within the trilayers. That means you have antiferromagnetic coupling between the layers. And you can see again in lanthanum, you have a pronounced specific heat anomaly, whereas in praseodymium, it's gone. You can see the resistivity on the left. Lanthanum, it becomes insulating below this stripe transition, whereas praseodymium has a nice cuprate-like thing, looks quasi-linear in temperature, except at low temperatures, you go over to T squared. Interestingly, in RIX, the RIX data actually looks quite similar between the praseodymium and lanthanum. So even though one has long-range spin stripe order, the other one does not, the inelastic magnetic scattering looks very similar. So what we were able to show is, in fact, with DFT plus U, this is a calculation that Antia did, that the sort of low spin metal state and the stripe state are very close free energy wise. It's very easy to go from one to the other. And people had originally thought 10 years ago it was a high spin state, but we now know that in fact it's not. You either get a low spin stripe state or a low spin metal state, and they're rather close in energy. So if you look at polarized X-ray absorption data, the nickel L edge, on the top is the, in red is a 438 lanthanum, in the middle is a 438 praseodymium, and the bottom is YBCO. And you see two polarization geometries, polarization in plane or along the Z-axis. You can see that YBCO looks very similar to praseodymium lanthanum. And what that means is the unoccupied states are primarily X squared minus Y squared. And so you get this sort of low spin X squared minus Y squared holes, somewhat reminiscent of what you see in cuprates. Superexchange has been determined by this RIX spectrum, and this is the magnon dispersion on the lower right that was determined by Mark Dean's group. As I said before, the lanthanum and praseodymium look very similar, except praseodymium is fuzzed out. And what you see is that you have a superexchange interaction, which is about 70 millivolts. So about half of that in cuprates, but still pretty substantial. And people have noticed that in the doped 112 materials, you typically see bond-centered stripes, whereas in this 438 material, you see diagonal stripes. But, you know, from old work that we did in the cuprates, the free energy difference between diagonal and bond-centered stripes is actually pretty small. And so it's pretty easy to go from one to the other. So in one case, you have a wave vector, say, near 1/3 0, and the other case is near 1/3 1/3. So wave vectors are saying you just rotate. You can see, again, this is susceptibility plots here for various tight binding dispersions. And you can see the susceptibility has a typically box-like structure around the gamma point, which basically means that there's not much free energy difference, say, between a 1/3 0 stripe and a 1/3 1/3 stripe. So now let me turn here towards the end to this recent discoveries, where we're going to have a lot of talks at this meeting. No one, based on the previous results on 214 nickelate, I don't think anyone really thought that we would see superconductivity in these Ruddleson-Popper phases. At ambient pressure, both of these materials, the 327, which is N = 2 Ruddleson-Popper, 4310, which is the N = 3 Ruddleson-Popper phases, have very pronounced density wave transitions near about 140 Kelvin. And they were substantial transitions, and so no one really thought that this would be a great place to look for superconductivity. But by putting these under pressure, what's been found in both cases is you suppress a density wave state under pressure, and lo and behold, the material becomes superconducting at around 80 Kelvin for 327 and around 30 Kelvin for 4310. Some of the earliest studies show some sort of finite resistance at low temperatures, but as people have made samples and better, the low temperature resistivity seems to go something close to 0 within resolution. So to me, this looks like the real deal. Let me remind you, lanthanum 4310, a lot's known about it. This is work that we've done with John's group over the last number of years. The Q vector is a 0.31, so slightly incommensurate. So it's close to being a 5-period stripe, but not quite. You have up zero down stacking within the trilayer. This is very unusual, right? So normally you would think about having up down up stacking, which is what you see in the reduced 438 material. But this one you see sort of up zero down stacking, which is very, very unusual magnetic state within the trilayer. We've looked for harmonics in the data. We don't see them. So it sort of looks like a sinusoidal spin density wave, sort of classic chromium-like. But again, the wave vector is close to being commensurate. So you cannot completely rule out, say, a 5-period stripe. Charge and spin turns on at the same temperature. They both look like they have an order parameter-like dependence. So it's not sort of like chromium where the charge is secondary to the spin. It looks like the charge and spin are turning on at the same time with more or less an order parameter-like variation. This is unlike cuprates where spin and charge seem to be separated in temperature. And again, you have a very pronounced specific heat anomaly, very comparable to what you see in 214 nickelates when they go into stripe order phase. Resistance has a pronounced anomaly at the stripe order transition. And so, but it goes from a metal to a metal. So it's a metal to metal phase transition. So in very recent work that Harry did with Antia, surprisingly, he found out that this so-called M0M state, where you have outer layers being antiferromagnetically polarized and the inner layer being non-polarized, is actually the lowest free energy state. It was very surprising. What happens is that there's a tendency for having a high spin state where the x squared minus y squared orbitals are aligned with the z squared, or a low spin state where the x squared minus y squared orbitals anti-align with the z squared orbitals. And what seems to be happening in 327, as you go from high to low, as you go in pressure, you drive from a high spin to a low spin, whereas you automatically get this in the trilayer, whereas sort of the outer layers are sort of behaving like high spin, and the inner layer is sort of behaving like low spin. And again, under pressure, you're probably driving the outer layers into a low spin type state. At least this is what seems to be going on. So very recently, this paper came out of the archive very recently. What they're seeing is in the 327 material, they're seeing something that looks commensurate. It's a 1/4 state, looks like a 4-period stripe, but then the resolution is somewhat poor. And why I say this is in 214 nickelate at 50% doping, you do have a tendency to see slight incommensurability, but it looks pretty much similar to a 4-period stripe state. The nature of this 4-period stripe state is being debated. You can have something like up, up, down, down. You can have up, down, zero, down, up. You can have all sorts of different kinds of 4-period states. And they've tried to use polarized resonant X-ray scattering to try to realize it. It seems to be this bottom state. As you go along here, blues are upspin, reds are downspin, and the black are non-magnetic states. So let me end with some questions here. So thinking about the reduced Ruddleson-Popper states where you're sort of going towards the cuprate side of the phase diagram, one big question is, can the trilayer material be electron doped? The nice thing about trilayer material is you can make very, very nice single crystals of this material. It's been a challenge to try to electron dope it. You can think about replacing the rare earth by some sort of 4+ ion. Think about intercalating lithium. People have tried to do this. It's very challenging. So to date, not a success, but people have been trying. Again, what's the best description? Is it charge transfer, Mott, Huns, Kondo, some combination of the two? Are the doped holes low spin x squared minus y squared like we expect for the cuprates? And how are the stripes in these bond-centered stripes in the 112 related to the diagonal stripes that we see in the reduced 438 material? So for the new materials, which are Ruddleson-Popper, I think one of the interesting questions is, what is a superconducting phase? It's been recently shown, and I think this will be presented here at the meeting. People have been able to do Meissner effect now, and it appears that the superconducting volume fraction is only about 1%. And that indicates to me that we probably don't know what the actual superconducting phase is under pressure. Do you have indeed a high spin to low spin transition under pressure, and therefore is superconductivity associated with low spin physics like in cuprates? A picture we've come up with is that the z-squared spins, the 3z² minus r², are basically background spins, where the x² minus y² can either polarize along or anti-parallel to the z² spins. But the basic physics seems to be like the low energy physics might be controlled by the x² minus y² orbitals. But a lot of people think that z² plays a fundamental role. And is these density wave state, is it itinerant like chromium, or is it sort of like local stripes like we expect for the LNSO compound, the 2,1,4 nickelates? And so with that, I will end.
Okay, great. Thank you, Mike. Any questions or comments for Mike? Yes, Ilya, please.
I have a question. Would you at this point be brave and say that the magnetic phases that you see, are these parent phases of a superconductor? What is your opinion?
You mean for double layer?
For double layer and for tri-layer, right?
Okay.
So
We're talking about the
spin density wave phase. Would you
the
think
Robertson
that this
phases? Yeah.
right?
So it
Would
does
you
appear
say
from everybody's data that you have these, in fact, you see from specific heat, it looks like a fair part of the Fermi surface is being removed. And you see zone folding in ARPES as well. I forgot to mention this. Dan Dezalle seen zone folding from ARPES. And for sure, the available data indicates that this density wave state is being suppressed by pressure. So in that sense, it sort of looks like cuprates. You have some sort of underlying spin charge phase, which you suppress under pressure, and then superconductivity emerges once you suppress this phase.
Maybe I can follow up on that. It's not obvious to me that this order is purely magnetic.
Right. So I forgot to mention this. So if you look at the tri-layer material, it's actually quite interesting. Let me come back to this. The interesting thing about tri-layer is even though the outer layers are polarized and the inner layers are not polarized, the data, if you look at the L dependence of the data, which is quite complicated, it looks like the CDW exists on all three planes. And in fact, the CDW, SDW have the same 2-to-1 wave vector ratio that you typically see in a stripe phase. That is, a charged wave vector is twice the spin wave vector. And the available L-dependence is, we have extensive L-dependent data. It looks like the CDW exists on all three planes, whereas the spin density wave only exists on the outer plane. This is not surprising from cuprates. You see this in cuprates when you have like tri-layer or 4-layer or 5-layer materials. Inner planes and outer planes behave differently. They almost behave like they are at different effective dopings.
But even for double layer.
Yeah, double layer is different because what happens in the double layer case, of course, there's only one type of layer.
Yeah, but I mean, even
I'm very surprised.
Go ahead,
Yeah.
Mike.
Yeah, I'm pretty sure what happens in a double layer case, okay, so that's something that's talked about in these papers, right? And so you can see that in this paper, you have the black things are magnetic, so you can sort of think of them like holes, and then you have the red and blue. So this sort of looks like a standard charged spin density wave stripe like you get in cuprates, but they've looked at other models where you say have up, up, down, down, which means that is a pure spin density wave with no charge component to it.
Mm-hmm. Yeah,
my suspicion is that you have both charge and spin.
Let's give Pinching a chance to ask the question.
Yep.
Yeah, so I was actually, sort of ask a slightly different question on Harold's compound. The recent debate about the charge density wave and spin density wave. So what is your opinion on I'm sorry, I'm not outside the field. That's why I'm asking this.
Yeah, this is a recent controversy, right? In fact,
yeah. So what's your perspective on that?
So one of the issues, right, is that this topotactic reduction is pretty drastic for the 112s. You're stripping out all the apical oxygens, and you go from nickel 3+ and nickel 1+. It's quite violent. And so there's been this debate whether this is really a true density wave or whether you simply have you have oxygen vacancies which sort of order in this pattern. And so there's still, and it's sort of like YBC, it sort of reminds me of YBCO, right? The density wave signatures are very weak, sort of like what you see in YBCO, whereas in the 438 material, the reduced trilayer, it looks very similar to like LISCO, LBCO, right? You have a very pronounced stripe state.
Okay, thank
So
you.
you see sort of the same kind of dichotomy that you've been seeing in cuprates.
Okay, Harold has
Weak charge
patiently
order
wait.
and strong charge order.
Harold, your turn, please.
Kind of jumping back to the discussion with Chimao, experimentally, theoretically, what would you estimate for the scale of for the trilayer, inner plane, out of plane doping level, or what is the degree of charge modulation in those two respective cases? Kind of 1% order, 10% order. Could you comment?
Mike.
Yeah, so this is the point. We're sort of putting a paper on this together, but I've been asking them, like, we need to have occupation numbers. We'll get them at some point. Of course, one of the problems you have in band structure calculations is the charge modulations tend to be weak because the Hartree potential really controls what's going on. It doesn't like to have different charges. So if you look at the 438 is a good example of that, where we looked at this extensively. It really looks like you have D9, D9, D8 stripes as far as the spin is concerned. But the charge modulation is actually relatively weak. But this is because in DFT calculations, the Hartree potential penalizes you from having a large charge modulation.
Maybe
my guess is the same thing would happen in these materials, but
I think we're running out of time. But I thought I would just add that if I look at the bulk accessibility data of the 327 across the transition, it looks complicated. It doesn't look like a canonical IQ magnetic order, but spectroscopy is coming out. Rick's from Donglai Feng and maybe other information will be forthcoming.
Yeah, I mean, the nice thing about 4310 is fortunately, we're able to take this data before the APS went down. So, I mean, we have tons and tons of data going out to high HKL. So the density wave state is known in great detail. The problem with the 327 is the crystals are very small, right?
Yeah.
So it's not been as easy to get data on the 327. In fact, in 4310, we also have neutron data, right? So
and inhomogeneity of samples.
So the samples are inhomogeneous. You'll hear about this, right? Something very unusual happens in 327. You get this polymorph where you have single trilayer. This kind of polymorph has never been seen in another Ruddleston-Popper phase before. So 327 is a very unusual material.
Is there any one burning question for Mike? If not, let's thank Mike one more time.
Okay, great.